Hey everyone. All right, so we can start. I'm Raj. I work at InVideo AI. InVideo AI is a tool to create and edit videos using natural language. So it's best for people who don't have any prior video editing experience. I mainly work with Elixir and Rust and a little bit of JavaScript here and there. And I help co-organize the Rust Mumbai meetup. So today, I'm going to be talking to you about the 1 billion rows challenge. I actually came across this challenge when, during a meetup, a fellow Rustacean excitedly shared their experience doing this challenge in Rust. And then I thought, why not try to do it in Elixir? It would be a perfect way to push Elixir through its paces, see what kind of optimizations we could do, and yeah, how much speed up we can get. So I decided to take on the challenge, but little did I know that it would lead me down to a lot of late night coding sessions and hunting down performance traces. But it was worth it. So let's take a look at what the challenge is. So you'll be given a file that looks something like this. It's a new line separated rows where each row contains the city name, then there's a semicolon, and then there's a temperature value for that particular city recorded at that particular time. Now, the it is guaranteed that the temperature value that you're going to get is always going to be a single digit decimal precision, and it's going to be between minus 99.9 and 99.9. And what our job is that for each city in the data, we need to calculate the min, mean, and max of for each city. Now, it might sound very simple. There are a few rules laid out, like you have to do all the computations at runtime. You can't use any external libraries, things like that. But yeah, that's pretty much the challenge, and it does sound relatively simple. But the gotcha here is that you have a billion rows of this, and you have to do it as fast as possible. And the input file itself is around 13 gigabytes large. So yeah, for the version one, I went with the simplest and idiomatic Elixir code that I could write. The kind of code that you write when you don't really think about performance and you just want to get something out working as quickly as possible. So this version is pretty simple. You just read the file completely into memory, then you split it by new lines, and then I'm creating a weather station to values map. So the map is going to have the weather station as the key and a list of values, temperature values as the value. And after that, I'm doing a single pass to kind of aggregate the result to create the final min, max, and mean values for each city. Performance wise, this code took 11.5 seconds for 10 million rows, 3 minutes 6 seconds for 100 million rows, and well, I could not run it for a billion rows because my operating system kept killing the process because it was taking too much RAM. So this was a good time to start optimizing. Um, right off the bat, I knew that simple tricks like using file.stream for streaming the file instead of reading it all at once would help. So I did that. And then instead of storing all the temperature values as list in the memory, I implemented incremental processing. So where we can store the min, max, sum, and count while we go iterate on the list one by one. After that, we do a single pass over the final map to calculate the whatever we want using the sum and count, which is the mean, and then we just sort it alphabetically and print out the result. This version took 7.8 seconds, down from 11.5 seconds for 10 million rows, 1 minute 24 seconds for 100 million rows, and around 14 minutes for a billion rows. So great, the 1 billion version is at least working now. Okay. So, oh yeah, and another thing I noticed was while just playing around with it, changing float.parse to integer parse took down the time from 8 seconds to 4 seconds for the 10 million version. I mean, of course, it gave incorrect values, but it highlighted that float parsing and doing the calculation with floats was a bottleneck, and we'll need to do something about it. Cool. Another thing I noticed while running these two versions was that my CPU was barely doing any work. This is a usage graph for the CPU while the code was running. The red line represents the start of running the script. So whatever is before the red is kind of like the baseline values, and whatever is after the red are the values, the CPU values when the script is actually running. So I thought, we've got all of these cores and they're barely being used. Let's just do something about it. And that's when I decided to introduce concurrency using task.async stream. The first change I did was I started using an ETS table for storing the intermediate results, because we are going to be updating it from different processes and we need a common storage for it. So simple changes to our process row function: you take in the ETS table and it checks if there is an existing record for the city in that table. If there is, then it will update the min, max, sum, and count. And if there isn't, it will set it to an initial value. Then, naively, I just changed stream.map to task.async stream, thinking, great, now we are concurrent. But well, I was wrong. What was happening was I started getting incorrect results. You could probably guess why. Because your temperature values for a single weather station can be in multiple lines at the same time, and then multiple processes are trying to override the same value in your ETS table. That was the problem. So there was a lesson learned that you have to be mindful of shared state and potential race conditions while concurrent processes. So I took a step back, rethought my approach, and separated the parsing and the processing. Because the parsing you can just do concurrently; it's independent, isolated from each other, whereas the processing depends on the shared state. So I separated that and then implemented concurrency for the parsing step, and then we are doing the processing synchronously right now. But the surprises don't stop here. At the start, I just implemented like concurrency for parsing each row. So one process for parsing each row, and thinking, more concurrency, more speed. But well, I could not be more wrong. So what was happening was I was creating millions of tiny little processes that was just doing parsing one row, and that was a problem because the benefit that I was getting from concurrency outweighed the cost that was needed to manage this process management overhead. That was another lesson. Too little concurrency underutilizes your resources, while too much leads to an overhead. So again, I implemented a chunk every sort of a thing, where instead of parsing a single row, we are now parsing 10,000 rows at a time. About the float parsing thing that I talked earlier. Here's a workaround to that. Essentially, what we are doing is, instead of parsing floats, we are splitting the float into with the decimal point. Then we concatenate the two characters, and then we take them to integer. So basically, 4.5, if you have, by splitting it with a decimal point, you'll get 4 and 5 in the list, and then concatenating it, you'll get 4, 5 as a string, and then two integer, you'll get 45. The rest of the calculations you do with the integer, and at the end, when you have to submit the result, you just divide it by 10 to get back into a float value. With all of these changes, here's the CPU utilization graph. At the start, we can see that we are utilizing the CPU more when we are doing the parsing concurrently, and comparing with V2, it is better. And finally, in terms of the performance, we are now taking 4.7 seconds for a 10 million rows, down from around 7.8. 46 seconds for 100 million rows, and 8 minutes for a billion rows, down from 14 minutes. But at this point, one thing was clear, that uh, I needed better instrumentation going forward, because I did not want to chase my own tail, generating incorrect results and things like that. So this is what I needed. I needed a way to check if the results that my code is generating are correct. I needed a way to kind of see if what if I needed a way to run the same code multiple times to find out what is the best chunk size that I can do. Then I needed a way to manage different versions in my code, compare those two versions, things like that. Finally, I needed to do performance tracing, find out what the bottleneck is in my code, and get the CPU usage measurement that we saw earlier. So I came up with a simple solution to all of this. I use Nix flakes heavily in all of my projects. This It's out of the scope for this talk, but please let's have a chat if you're interested in it. So let's see. For the versions, I have all of these different versions in the code base, and then there's a single file which essentially takes in the count and the version, and then runs that particular version with that particular count. What is count, you ask? So I don't want to run the 1 billion file every time just to see if it's working, because I want to be able to iterate quickly. So count is the number of records that I want to try it out with. So I can just try with 1 or 10 or 10,000 to see if it is working or not. And the way I run this is, essentially, I have a simple shorthand called run process measurements. So what I can do is I can do run process measurements, count 1,000 and version 3. So it'll take the 1,000 measurements file, it'll run it, and it'll make sure that it'll verify if the result is correct. The way this happens is I have this run file. Actually, let me show in the light mode. I guess that would be better. I can't. Cool. I have this bin a run file which is injected into my shell, and what it does, it parses the count and the version using shell script, and then injects that in mix run, which just calls the that function that we saw. Finally, for the CPU measurement, let me show that. I have a simple shorthand again called run with CPU profiling. So what I can do is run with CPU profiling and then give it a command. It'll establish a baseline for 2 seconds. The way it does that is I have the simple file, which it waits for 2 seconds, and I'm using top to get the CPU measurements. And then finally, once that's done, it prints a graph like this using the GNU plot uh, thing. Okay, coming back. So yeah, with that, I was able to iterate quickly and have a good, solid foundation to work ahead. Regarding profiling the code, I had a few requirements. I wanted to pinpoint what are the time-consuming code sections. I wanted to detect performance bottlenecks. I wanted to know what the frequency and duration of the function calls were. What is taking time. Also, a flame graph like visualization would be nice to like kind of measure the impact what the optimizations are having. Elixir has a number of tools we can use to optimize or to profile the performance. The simplest one is cprof. It just counts the function calls. It gives you a quick overview of what the most called functions are. It's very lightweight and it does not have any minimal impact. It does not slow down your code. Here's an example of a cprof output. We can see that we are hammering the string functions a lot, but function number of function calls only tell one part of the story. The other part is execution time. That's where eprof comes in. It provides a clearer picture by giving the number of function calls as well as the execution time. So over here we have an example output of eprof. We can see that the readline file functions and ets functions are taking up a major percentage, like 5-6% each of the time. While I was searching for kind of combining all of these two into a nice looking flame graph, I found eFlam. I hope I'm pronouncing that correctly. Please correct me if I'm wrong. But it's amazing. Like, it's a tool which generates very nice looking flame graphs like this. Let me show an example. Yeah. And over here we can just zoom in and we can see what the what the hierarchy is of the code that ran, and we can see how much time each block of code has taken, things like that. Pretty cool. Finally, okay, these are the examples. And finally, there's Benchy. Benchy was very useful in terms of comparing the performance of different pieces of code. The logo is not the Benchy logo. Uh, it's just something I generated using AI. Yeah. So it compares different pieces of code. But yeah, feel free to use that if you like it. It compares the performance of different pieces of code. It runs each of your functions with the given amount of time after an initial warm up, and it'll measure execution time, optionally memory consumption if you want, and it gives a plethora of statistics. Average, IPS, median. It's amazing to understand the performance characteristics of your code. And if you like visualizations, who does not, you get different plugins for creating different kind of reports. Here's an example comparison report between two versions. We can see it's showing me which version could run how many iterations. And if you click on each one, you'll see detailed infos about each of them. Okay. So now that we have seen that, coming back to our problem, until now we only had concurrency limited to the parsing step, whereas the processing step was completely sequential because of the shared state. Just to recap, this is our main function, the process row function, and it needs to check if an existing record is there in the ATS table to generate the new output. So I thought, well, what if we could do something like this? Like, we divide the whole data into different chunks, and then each chunk can produce its own result independently. And then at the end, we try to combine and merge the whole thing for the final output. So this is the change that I did to the process row function. It now takes a map instead of a ETS table, and it just updates the map with the updated value for each record. Then In before we were doing the process row synchronously. Now we have an async stream for that as well. We take the chunk of rows that we have, the 10,000 rows, then we do a reduce over them to kind of get the updated record. So this interim records map will now have the result for this particular chunk of data. We will insert that again in the ETS table, but with row index as the key. Row index is what I'm getting from stream.withIndex, and this will ensure that we are not overwriting the same data and we are not causing race conditions. So after this is done, we run a final pass again to kind of merge all of the outputs into one. It's pretty simple. We have a final accumulator, and then for each city, for each intermediate result, we just check if it exists in the final accumulator and just merge them if it does not. Okay, so CPU usage wise, we are doing a bit better than before. Now the CPU is getting used even in parsing step as well. Still a long way to go, but better than before. And performance wise, we are now 3.3 seconds for 10 million rows, 33 seconds for 100 million rows, and 5 minutes for a billion rows. Cool. So let's analyze the flame graph of the version that we just ran. If we go here, I think this is the one. All right. So we can see that at the start, there's this big chunk, something is going on. A lot of things are going on over here. And we can see that there's, this is all file.stream that's doing this. There's io.bin read. Then at the end, we are doing read line, things like that. Then after that, this is the parsing step that's happening. So if you zoom in, we can see this is the parse row, and then we're doing split, trim, trailing, things like that. And they are taking a big chunk of time as well. Individually, they are very inexpensive, but we are literally calling them a billion times. So any savings there will help us. So then I thought, how can we optimize these things, string.split, or basically string operations? And pattern matching is what comes to mind because it gets optimized by the compiler itself. So this is what we are doing. We have, this is a sample row that we have. We have a city name, then a semicolon, and then the temperature value, and then a slash n. Because there's a slash n, we are doing trim trailing, and then we concatenate them and do a string.to integer. To think how to optimize this, I decided to see what string.to integer is really doing under the hood. So let's go to the Elixir code base. We can see that to integer is essentially calling Erlang's binary.to integer. Let's go there. Erlang's binary.to integer does some checks on the base and then calls the ERTS internal binary to integer. Let's go there. We are in C land now. Again, a bit of more checks, and then it calls chars to integer. Let's go there. Chars to integer does a few more checks, trims any leading zeros, and then finally calls C2 int digit from base. Let's go there. Um, and okay, so now we are here. The purpose of this function, C2 int digit from base, is essentially to convert a number characters into its numerical value. So what it does is, if it is less than 9, which means it has base 10, it will subtract 0 from it, which is, if you remember from your computer science undergraduate class, it has ASCII value 48. Okay, so in Elixir, we can use the question mark operator to find out what is the ASCII value of a character or a code point, to be specific. So question mark 0 will give you 48, question mark 1 will give you 49, question mark 2 will give you 50, so on. What we can do is we can use this to get a numerical representation of a given character number like this. We can just subtract 48 or the ASCII value of 0 from it, right? Okay. And our temperature values are very consistently structured. There's a decimal point and there's a digit before and a digit after. Then we can use something like this, which is a pattern matching function head, to detect the first digit, then there's a decimal, and there's the second digit. And whatever is rest, we just ignore. Whatever is rest is slash n, and we just ignore that. So a good thing here is we don't even need trim trailing because we are just ignoring it in the function head. And after that, we use the char to num function to kind of convert it to the integer value. So this was for 4.5. We can have similar function heads for different styles as well, minus 4.5, 4.5, 45.3, and minus 45.3. Because we know that our input is very structured, there aren't going to be any invalid output inputs. We can just skip all of the extra things and jump directly to parsing the number ourselves. Okay. So over here, we are seeing 3.1 seconds for 10 million, 31 seconds for 100 million, and 5 minutes, 19 seconds for a billion rows. Okay, could be better. Again, what can we do? Let's go back to the performance trace. We can see that at the start, there's this big chunk of the trace that I'm not quite sure what it is doing. I know that there's parsing, then there's processing. What is this guy doing? So if we zoom in, we saw that it was the whole file.stream was essentially causing the whole thing. And why are we using file.stream? We are using file.stream because we can't load the entire file into memory. We want line by line. We want to process it line by line, and file.stream does that for us, which is very convenient. But the problem is we are seeing a lot of footprint in our performance trace. So what is actually happening is, because we are reading it line by line, we are running into something called as thrashing over here, which is essentially when a system is reading too small of an input, and it's essentially spending too much of a back and forth between storage and the program, right? That's the problem that's happening. Well, I just thought, well, why not just read bigger lines? Instead of reading a line, let's read bigger chunks of bytes. The problem there is, because file.stream gives us line by line input, this is a kind of input that we get. We are sure that in each line that we get, we are going to get a city name, there's going to be a semicolon, there's going to be a temperature value, and a slash in every time. If you read a fixed chunk of bytes, well, all bets are off. You might get incomplete measurements. Half of your measurement might be in first chunk, other half would be in second chunk. You can't do concurrency when you get incomplete measurements. So, well, what can we do then? So I saw that there's something called filed readline and primfile.readline in the stack trace. So I went ahead and searched about it. I saw some people talking about getting a lot of speed up by doing primfile instead of file. And the reason that file abstraction exists is to support like machines with diskless machines which do remote file server. That makes sense. Then I went into the primfile code base. It's internal and undocumented, but here are the most important functions that it has. First one is a simple primfile.open, which just opens a file and gives you back a file descriptor. A file descriptor, you can think of it as an internal representation of the file, which stores some metadata, like where in the file, what is the current position that we are reading or writing at. Then there's readline, which takes your file descriptor and then reads from the current position until it encounters the next new line character. And then finally there's read, which essentially just goes from the current position and reads the number of bytes that you have asked it to read. And then of course all of these update the new position in the descriptor as well. Okay, so now you probably know where this is going. I thought, why not take the middle road? You just use read to kind of take in a fixed number of bytes, and then use readline to make sure that you have a complete measurement. So we don't need to do readline every time just because we need complete measurements. So let's implement that. Just as a recap, this is the current version. We have a file stream, and then we do task.async stream. Now I have a new function called read and process, where I have this chunk size, and then I do a primfile read with that chunk size. And then after that, I do a read line just once per chunk size to make sure that I have the complete measurements. I concatenate them, and then I spawn a new task to process that particular chunk. And once I spawn a new task, I go recursively call myself for reading the next chunk of data. Up at the call side, we get an array of tasks back because we have spawned those. And here we just essentially do an await many to make sure everything is done before proceeding further. And what we do after that is simple, what I've been doing so far. Just read the ETS table and do the reduce them to the final results. Okay, so this is the result that we saw. uh, we are now at 0.6 seconds for 10 million rows, 8 seconds for 100 million rows, and 1 minute 21 seconds for a billion rows. That is something that gets you going. Okay, cool. Let's look at the CPU usage. What a beautiful graph. We're going. This is the first time I saw 100 on that graph. It's shooting up right when the script starts and only coming down when it's completing. Compare it to the previous ones, which was not that good to look at. Here's a benchy comparison between V5 and V6. We can see it's running a lot of iterations per second, and I can also see that it's consistent. It's not a one-off case that I'm showing you. And yeah, the large thing that we saw earlier in the performance trace is now gone. It's just compressed into one because we are just doing read line once per chunk size. Okay, cool. But another thing that caught my eye was now there are a lot of task.async calls in here. Because if you think about it, for every chunk, what we are doing is we are creating a new task using task.async and then at the end just awaiting for them. So what we are asking the beam to do is create a process, then do the job, and then the process dies, right? Which is cool, but why, right? We know how much work we have to do, we know what our chunk size is, so we know how much processes we need, so we can just have something like a reusable worker pool where our workers ask us for jobs, we give them the jobs. Once they are done, instead of dying, they'll ask us for new jobs. We don't need to have that overhead as well of killing and creating a process. So that's the direction I went in. We can use a fixed worker pool, reuse workers, and minimize the overhead. Okay. Okay, so here's the concept. We'll have something of a parent process of sorts, which will spawn worker processes at the start. Then each worker will send a give work message to its parent. The parent shall give the work to the worker, and then worker will process the chunk, write the result, and ask again, hey parent, give me more work. This will go on until there's no more work to be done. And at the end, again, we just collect it from each worker. Here's the implementation. This is the worker module. Uh, at the start, we are sending a give work message. Then we go into a receive loop. We are back at the absolute building block of Elixir, which is processes. We go into a receive loop where we wait for a do work, and once we get the work, we do the work and just call ourselves again. Um, Except when we get a result message, we will send the result to the parent and then not call ourselves again and just die. Then the process chunk, we are doing a binary dot split, um, which can be optimized actually. And then we are just parsing and processing at that point. Yeah. At the call side, we boot up the workers, and then we open the file, we go into read and process, and in read and process, we do the same trick. We do a prim_file.read, prim_file.readline, get the whole data, and then we send it to a worker. Okay, how to send it to a worker? We can't just send, we have to wait for the worker to tell us that it needs work. We go into a receive loop, it will tell us that it needs work, and then we do a send to the worker. After that's done, we recursively call ourselves because this will just happen until the file has no more data. That's when prim_file will give us an EOF, and that's when the recursion will end. Okay. And again, at the call side, once this is done, we wait for a give work message from all the workers. So you can think of this as sort of a task.await many version equivalent that we had before. Okay. Then we just ask each worker to give us their result. Another change I did this time was, instead of an ETS table, I started writing to the, actually I can show here, I think. Yeah, I started writing to the process dictionary of each worker, because since we are not killing the workers, we can just use their process dictionary instead of an ETS table. We receive the results, and then yeah, we just close the file. Yeah, so this was the CPU usage graph. Again, very beautiful, goes up, comes down only once it's done. Comparatively, it's faster. How much faster? So we went from 0.6 seconds to 0.3 seconds, 8 seconds to 3.6 seconds, and 1 minute 21 seconds to 32 seconds for a billion rows. Amazing. Okay. Yes. Oh yeah. And I also use Benchy again. I mean, I've been using Benchy for each version, but here's where I decide to show you. I used it to find what is the optimal chunk size. Because it's a trial and error thing. So I just make the code take in the chunk size as an argument, and in my Benchy script, I tell it, run it with this chunk size, run it with that chunk size, and then I can get a definitive measurement that, hey, 1 MB chunk size is the best. Cool. Yeah, so that is what bothered me at that point now. We are still doing a binary dot split over there, which can be optimized using uh, pattern matching. So, all right, how do we do that? So this is the code. Now our parse temperature function ignored the rest, But instead of ignoring the rest, what we can do is we can make it know about /n and pattern match on that, and the rest we can just pass along recursively. So in addition to parsing the temperature, parse temperature also now has the responsibility to kind of get the whole recursive chain going. Yeah, and it calls process chunk lines with the rest after it's done processing the current digit value that it is currently processing. Then process chunk lines initiates the recursive chain over here, calling parse weather station. Parse weather station has two pattern matching heads. So it starts off with the whole binary, the whole data. Then it tries to find where the semicolon is. The way it does that is it will come here. It will see if the first character is a semicolon. If it is not, then it will call itself with the rest thing and the count. And then when it does find the semicolon, well, we can just use the count to split the key and the temperature binary and then call back the parse temperature function. Oh yeah, by the way, the documentation for the binary macro was super helpful in understanding all of these binary size and all of the weird pattern matching tricks that are very performant. Okay, so with this change, removing binary.split completely, we went to 24.7 seconds for a billion rows, 2.46 seconds for 100 million rows, and 0.25 seconds for 10 million rows. So throughout the journey, we have gone from around 14-ish minutes to 24.7 seconds for a billion rows. And for me, this whole journey was, in addition to just having more speed and reducing the time, it was about developing a performance mindset. It was about understanding the true cost of the code that we are writing and what are its performance implementations, performance implications. I mean, of course, I'm not saying we go and now we rip out all the Elixir modules and write our own number parsers. But the most important thing to ask is this code worth optimizing? More often than not, the answer is going to be no. But when the answer is yes, that is when the real fun begins. Recently, I was working on a project where we had to analyze a video for the user while the user is wetting. So a 1 hour video at 30 fps will be around 108,000 frames that we have to analyze. And the experience while performance optimizing this challenge was very helpful in optimizing that kind of scenario. Another example I can think of is we had to write a RLE encoder and decoder. RLE is essentially run length encoding. It's a way to compress binary masks, background masks, so 0 or 1. It's a way to compress background masks into a small format. The tricks that I learned of the binary pattern matching tricks that I learned over here were super helpful in fixing that and making that as performant as possible. So yeah, the takeaway I guess here is optimization is an iterative process. It's very important to understand what are you trading off against, and most important thing is we have to use the profiling tools effectively. I do encourage you to try out different challenges like this. It's not just about which language is faster or how much speed we can get from a particular language. It's also about understanding our tools better. With that, I'll stop here. Thank you.
All right, thank you. We have enough time for questions as well.
Yeah.
So if you have a question, raise your hand, please. And if not, we already have one or two coming in from the Hoover app. Have you measured, I think, compared your implementation against frameworks that are specifically built for this use case? So Apache Spark and Flink are the first one to come to mind.
I have not. I've also been wanting to do with Flow, the Flow Elixir library, but I have not done that. But I imagine those would probably be faster. I don't know. We'll have to check.
Yeah, and you answered the second question already. Have you tried this challenge further by comparing your results with using extra dependencies? But the challenge is not using extra dependencies, so that would kind of defeat the purpose. But that would be interesting. Any more questions? Yes.
Did you consider doing a process per city?
A process per city. Oh, that's an interesting idea. I did not do that because you don't know how many cities there are going to be in your data. But yeah, we could try that out. Yeah, I will try that out and let you know. Yeah. But how will that help us? Could you elaborate in terms of performance?
You wouldn't have the roll up at the end because you'd just be maintaining the statistics on a per city basis,
Right. Yeah,
right?
fair.
And you could spawn, well, you could name the processes. So for when you do the parsing, I don't know, maybe it wouldn't really make much of a difference now that I'm sort of thinking through it, but that's why I asked.
But yeah, it's an interesting idea. I'll give it a
Yeah.
shot. Yes,
Okay.
thank you.
Yeah.
Just a question, if I understood it correctly. Did I get it right that your last solution scales linearly? So it's a factor by 10?
Yeah.
Excellent, amazing.
Yes.
All right. Any more questions? If not, then I have a final one. I think one of the nice things of conferences is that you can meet people in person. And you actually mentioned a few times that you're using Benchy in your talk. The creator of Benchy is also in the room, Tobias.
Yeah, that's why I was a bit when I used the fake logo. I tried to find a logo for Benchy. I couldn't. Yeah. Yeah.
Yeah. So the question that I have for you: do you have any requests, or do you only have praise for Benchy as well?
I only have praise. Yeah. Thank you.